Greetings all. So we kind of reached the last topic of our course, and I decided to take actually something a little bit different than the original syllabus would have asked for. I think this is more interesting, and also we have talked about this, and we need to talk a little bit more about it. You see that I'm actually though jumping to a previous chapter, to chapter 10 on graphs, but we use some stuff of trees, so it's good to do it in this sequence. And so graph coloring, and what is this about? And so this is my last topic. So I'm gonna assign homework problems for it. So that's still there, but we won't have a time for a quiz anymore. All right. So we know what the graph coloring is because we talked about it. Remember, I remind you. So for instance, if let's take a simple graph like this here, something like this. Okay. So what is a graph coloring? Is you give a color to each vertex so that, and the condition is only condition, no adjacent vertices have the same color. Okay, and so for instance in this case we would make this red, but it is clear that we always need at least two colors, right? Well, except for if we would have just a single vertex, yeah. But a real graph, a graph with edges and stuff, we will need at least two colors, okay? Because there's an endpoint and a beginning point, and the two endpoints. Sorry, there's no two endpoints, and they have obviously must have different colors. So the question is, can we do just with two? Right, and we have talked about this. Like for instance, here you have to make this green, but now you run into a problem. You cannot make the next one here this red, so we need a new color. So we need to make it blue, and then we can color the next one here with whatever we want. We can use green again. So we see here that two colors with this graph, two colors don't work. Okay, because the reason is, well, let's how do we are we sure that two colors cannot work? And that is that's why I want to put this after trees. We talked about backtracking, so we can try to backtrack in our coloring here and see perhaps we should have made a different choice here. So we had this one and then this one, right? Okay, we should have made a different choice in. Oh, I see. This is back on a much bigger thing. All right. Well, we start with we can pick any two, and two vertices, adjacent vertices, and give them different colors, and then we gave this vertex the first possible color, right? We can order the colors. Let's say let's put red. Give red priority over green. So we try to first make this red, but we cannot. So the next available color is green. So that is the backtracking method that tells us to do this. And then we try to look at the next vertex, that is one of the vertices that is adjacent to it. The order in which we do it is again not really important, but we have to stick to a certain order so that we know how to backtrack. The order in which we run through we'll want to color each of the vertices is the only thing that we need to keep track of, is that we look at all possibilities. In other words, that we make a full decision tree, that we cover everything. So we see that we give this green, and then we say, what color can we give this? But at this point we see there's nothing we can do anymore. We had no choice about this because we cannot take red, and then here we have no choice anymore. So backtracking doesn't tell us anything more here. We know it cannot be done with two. So two colors doesn't work. So let me do again what the coloring that we had. So we see we need three colors, right? And notice that there are different ones. The previous one I had the green one there on top, and now I make it red, right? The coloring is not unique. Two doesn't work, but three does. And so the least number of colors that we need, we call, so this is the definition, the chromatic number. So this is the graph G, we call this with a Greek chi, so this is the Greek chi, and this is called the chromatic number, and that is defined as the least number of colors necessary. The least number of colors that you need to color the graph. Let me not write that up. And this just a little bit know where the word comes from. It's always nice to know why something is called the way it's called. Chromatic, chromos, refers to, is Greek for color, right? So chromatic means coloring number, and in Greek we have a letter that's called ch, and it's pronounced kro. In English we say kro. In Greek one might say kro, and this Greek letter is represented exactly by this first letter. So that the use of this chi, this Greek letter chi, which looks like a bit like our X, but it's not pronounced like an X. It has this curly, so it looks a little bit more curly, like on one. So this would be an X, and this is a chi. Okay. So that's the chromatic number. And so what we can conclude in this case is that the chi of this graph is 3. We know that the chromatic number is at least 2. And now coming back to why, when we first talked about coloring, we saw that the chromatic number is 2, even only if this means that the graph is bipartite. Remember this? Okay, we did even this in a quiz, I remember. So if you can color with 2, there's a bipartite graph, otherwise it's not. Okay, and so the G that I had drawn there is not bipartite. Okay, so let me do another example to show you, to figure out a little bit how to, it's not so easy, by the way, yes, I should say, to know whether, if I give you a graph, whether you can, how many colors you need, what's the chromatic number of that graph, we at the moment have no fast algorithms. So this is considered an intractable problem. It's exponential in the number of vertices, because we basically have to try every possible coloring. We basically do the backtracking method, which means that we have to consider all possibilities. And that is, unfortunately, takes way too long. And I will come back to this problem of coloring, finding the coloring number, because it's an important, it can be used. We'll see how we use it. But before I do this, I want to show you some ways that we could calculate this and what it gets involved in there. So here is a graph that I constructed. So let's make it this, it's 6 vertices. Yeah, of course. We know that the chromatic number is never going to be more than the number of vertices, because we just could color every vertex in a different color, right? So we know at least the chromatic number can never be more than 6. You might say, can it be that bad? Yes, it can, and I'll give you an example in a sec. But let's now look at something that is not that bad, but it's still not that great either as far as chromatic number is concerned. So here are my edges. I'm copying this from my, let me make sure that I don't, like this, and then a connection like that. Okay. So let's use backtracking, but I'm not going to make the actual tree. I'm just going to do the backtracking with my undo button. Okay. But that's still, it's doing that way is a little bit dangerous, in the sense that I might forget that there's other combinations. Okay, so what I'm going to do is I'm going to try to do these, color these in the following order. So from left to right and row by row. Okay, I'm making myself fix the order so that I will try every possible combination. Okay, so we know that we need at least two colors, red and green. There is no doubt about that. So, and perhaps, again, let's make an order in which we try to color. Okay. So, again, to be systematic, I need to have a method to make sure that I try every possibility. Okay. So, let's go to the next one that I said was the next row, the left one. What is my first color that I can use? I cannot use red, so the first one I can use is green. Okay, I try that. So I'll make this green. Okay, what's the next color? The next one would be this guy, and I can use my first color. I can make it red. Okay, so make it red. Okay, going down to the bottom, to the left, what can I do here? Well, I see that both red and green are no longer available, so I have to come up with a new color. I have to use a third color, so this chromatic number is at least 3, so here we go. This is blue. Sorry, I forgot one edge here. There's an edge here, sorry. That's gonna be the problem. So I make that blue, and let's go now to the last one. And you notice that I cannot use any of the 3 colors that I have, because there's a blue, a green, and a red neighbor for this guy. So I have to come up with yet a fourth color. So let's call this orange. Okay. So at this point, it seems I need 4 colors, but perhaps that is not the optimal strategy. This is not the best thing. So let's backtrack. Where can I backtrack? Well, there was no choice in this one, so I have to backtrack at least one further. Okay. Oh yeah, sorry. I'll fix this. So I have to fix this, but I'm going to backtrack further, because this one I could have made a different choice here. No, I had to take the next available color, and it doesn't matter here whether I have to take a new color. That's the point. So even this one, I have no other choice. I can choose a different color, but that's not going to help me, right? It's the third color. It doesn't matter which one that was. So I have to backtrack even one more. So that is this one. Perhaps I should have recolored this in a different way. So now let me put this back in here. I should also now, some things have gotten in the meantime also backtracked. Okay, so now, so okay, so right. We backtrack to this way, which we had colored to be red, and we said perhaps that was not smart, so let's take the next possible. We cannot take green, so we have to take blue. Okay? Okay, we give this blue. Alright. What can we do now with this one? We cannot make it red, we cannot make it green, but we can make it blue. So let's take it blue. Right? Blue, I feel, yeah, that's correct. So now what? The last one I can color red. Okay, so what seemed to be the best choice, taking using as little colors as possible, right? So at this point I was not forced to take a third color, but if I did not take the third color, then I run into problems. So by taking a third color, I showed that they actually can use now only 3 colors. So this graph has chromatic number 3. In spite of the naive attempt was failed, but by backtracking I saw that it was a different attempt. So that's just what I'm trying to show, is that this is not such an easy problem. Okay, it turns out to be 3, but it is not obvious that this was 3. But in particular, we know it's not a bipartite graph. So I said this here. We know that the chromatic number is at most the number of vertices, right? Can it be that bad? Well, yes, it can. So remember K5. What is K5? This is the complete graph on 5 vertices. So here we go. So that means every 2 vertices are connected. I think I got everything. Yeah, I have to have a pentagon inside the pentagon. Right, okay, I got it. So now let's think about what can I do here. Well, at the beginning we have always these two colors. Now the next vertex, no matter which vertex I pick, it is connected to these two vertices because the two colored vertices already, because it's a complete graph. So this has to be a new color, right? This has to be a new color. But now, if I pick one of these vertices, doesn't matter which one I pick, whatever I pick, I cannot use any of the three previous colors because this connects to each of them. It's a complete graph. So I need a new color. So let's make it orange. Oh, that didn't work. What happened? And then the last one, same problem. It connects to every other vertex, so any of the existing colors cannot be used, so I have to do a last one, and let's make it yellow. So here we see that the chromatic number is 5. Okay, so it can be as bad as the number of vertices, and it can be as good as the number of as 2, that's namely the bipartite graph. So it's between 2 and the number of vertices, and somewhere in between are all the possibilities. Okay. So, what I want to say. Okay, let me do one more example here. It's going to take a little bit of time, so let's it's an example also from the book. Now let me make my things in this. So I have one. It's a rather symmetric picture, so I'm gonna. Okay, so we have the contours, and then we have this down and down, and we have the diagonals. Okay, that is one graph, and there's a second graph in which I will, so I'll do this I'll put it for the moment here, but I will erase it now. So there's a graph where I do one more edge, and I want to show that these two graphs have different coloring. Now, let's first think of what we for sure know, is that if I can color the big graph, let's say with 6 colors, then I know that removing an edge, I'm definitely going to be able to color the smaller one also with 6, but perhaps with less. Okay, so the number can never go up if you erase edges, obviously. Okay, so let's go back to the original graph that I want to color, and let me put my colors in an order that I'm going to take this one. I'm going to take green, blue, and if necessary. No, yellow is not so visible, right? So I'll do this one. Okay, so this is the order I'm going to use. Okay, let's start. It doesn't matter which I take. I take these two here. Let's take. I'm going to go again from top to bottom, left to right. Okay, just to have some order. So I start coloring these two. Okay, now I have to color the left, this one here. Well, I can use green. So let's use green. Okay. So what about the following one? Well, that one I cannot do green. I cannot do red, and I cannot do green. So I have to use my third color, so I'm going to use blue. So this becomes blue. And what about the last one? Oh, I actually have choices there. I can make it red or blue. So keep in mind, whenever you have a choice, okay, you could say, okay, you had a choice here, choosing the color you wanted, but that's not really a choice. I have to use a new color, and then that is the color blue. So this is the first part that I had a choice. Well, here are two. Here I had to choose two. I could have used the green, or I could use already the new color. So if I backtrack into this, I have to backtrack further down. But if this one, I had a choice. So let's yes, you have a choice because I can make it either red or blue. So I'm going to make it red because that's my first try. Okay, I make it red. So, okay, now go to the bottom, I. In the bottom, it is clear that I cannot use it's clear that I need even a fourth color, right? So, because all the three different ones, so I need this color here. Now, I'm going to try to, what my goal is, I know it's at least, we know it's not 2, right? We saw at this point that 2 doesn't work anymore. So we know, we are now trying to stick to 3. So let's try to not use the orange. So I have to backtrack until I prove to myself that 3 colors doesn't work. So I don't want to do this, so I backtrack this one. We said we could backtrack this color and perhaps try a different color. There was another choice, we can take blue here. That's the next backtracking that we could do, right? Remember I said that? So we could do blue here, but that doesn't make any difference to this vertex because it doesn't affect it. So this choice, although also valid, doesn't help me, so I have to backtrack even further to the next one. Here we argued it doesn't matter, we shouldn't try anything else because we are trying to only work with 3 colors. So the next one that we backtrack to is again the corner one. Here I had a choice. I chose to get my first available color, this one, green, but perhaps I should have taken blue. So let's take blue. Okay? Now, okay. What about this one again? Well, I cannot use red and green, and I have to take blue in this one. So I'll take blue, okay? So here again, there is no backtracking. To this one, had no choice, okay? And now to this one, there's also no further choice, right? If I have to backtrack all the way to here, then I'm lost. That means I can never do it with 3 colors. But let's continue. What about this one? Now, I still have two possibilities. I can use red or I can do blue. So let's use the first possibility. Let's use red. Okay, so I'm going to use red here. But remember, so now I should backtrack to this guy. I can backtrack to this one and replace this by this color. Okay, go to this one. Oh, no problem. I can make it green. Okay. And that's the only choice I have. So if I ever have to come back to this one, I should continue because there's nothing else I could do here. And now what about this one? Well, to use a word, I'm screwed, right? Because I have to use a 4th color, so that doesn't work. So let me, okay, just to see the animation, right? So I'm doing this, so it's not good, so I'm backtracking. I said, this green one, I had no choice. That I had to put, if I'm trying to put in 3, I had to put green there. So backtrack to the previous one where we did have a choice. Here I could have chosen instead of red, I could have taken blue. So let's try that, perhaps that works. So I take blue here. Okay, so now what? Okay, the bottom left one, I can make, there's only one choice, so I know now that if it doesn't work, then it won't work. I have no choices left anymore, so it better works, but luckily it does, because I can make this one now red. Okay, so this shows to me that, first of all, I prove basically that this is the only solution, right? Because as I remember at some point I was saying, if this doesn't work, I know it never will work because I've exhausted all possible colorings that I could do. I really made a full tree. I didn't draw the tree, but I hope you followed that I did every possible choice that I could make. So the conclusion is the graph has chromatic number 3. Now let's go back to our the bigger graph that we make, this one here. So what's this? Let's call this H. So H is the same graph with this additional edge. You think, what is the chromatic number of H? That is now the question. And I claim it cannot be, well, we know it has to be at least 3 because it cannot be less than, right? Otherwise, if we could do it with 2, then we could, in removing the green edge, you would have a graph that can also be colored with 2, but we know it cannot be done. But the coloring that we have obtained of the previous graph of G was basically the only choice. We had to color it this way. Therefore, if there is a coloring with 3 colors, it must, of H, if we can do the same for H, it must be, these vertices must be colored this way. But that is not a valid coloring, right? So we see that the H cannot be colored with 3. Because, I repeat, because I backtracked, And I found the only solution, because I basically drew the whole tree, and I was so lucky that at the very final leaf, I did get a solution. So there's only one solution, this solution. Therefore, if I color the big tree, it doesn't matter how I color it, this one has to be colored this way. I have no choice. If I use the three colors here, it has to be colored. If I'm trying to use three colors, then this is how the inside part, this black part has to be done, and therefore there's no way this is not a valid coloring in the bigger one. So we see therefore that this must be bigger than 3. Now, it doesn't necessarily mean that it is 4. It could be even that by this one edge could really make the whole thing blow up. But let's see. Where do we have to start? If you remember that we were backtracking, right? So we have to backtrack to the first time that we get a conflict, to this conflict. Yeah, this was where the first, remember, I always went from left to right, so backtracking is from right to left. So I'm going through this, I'm going through this tree this way, right, to the vertices. So this one and this one, and this, I backtrack to this one because this is the first time that I would have a conflict. So here I know I cannot do it with 3, so I have to try the 4th color. Let's see whether it works with that 4th color. So I put the 4th color here, okay. And now it's actually clear that there's a solution, because I can already take the previous solution that will work, right? So that would be green here, I guess. The first thing I could do is green here, and the next thing I could do is red here. So this does work. So we have a coloring of 4. So the coloring of H is 4. So somehow, therefore, I try that. I hope that this kind of brings the point that I want to bring down up here is, it's not so hard to show that the coloring of a graph is at most 4, at most 5, because you just have to provide the coloring. So here, this coloring shows that if you just come to the video now, you were dozing off and you didn't see anything, and you just see this and say, okay, yeah, I see there are 4 colors, so the chromatic number is 4 or less. The hardest part was saying there is no less. That is actually the harder part. This one, once you have the coloring, you just count 1, 2, 3, 4, and you know. Okay, so that is an example of something that is, you see how many vertices we have, with 2, 5, 7 vertices, and we had 4 coloring. So it is really not much that you can deduce. We cannot, as I said, the problem of finding the chromatic number, how many colors there, the coloring problem, is considered an intractable problem. Now, this all goes back to an old problem. This is what is called the 4 coloring problem. And there's an interesting history, I'll tell part of it, but there's much more in the textbook about this problem. So a student was looking at a map, and so I'm going to draw not a realistic map, but kind of a map. So I'm talking about a map here. So suppose these are various counties. That was actually what he was looking at. He was like looking at counties in the UK. And so it was something like this. There was a guy here. Okay, yeah, so we had the region, let me call the regions A, B, C, D, E, F, and G. Perhaps not a very realistic map, of course. I mean, I don't know any country that looks like an egg, but let's now think that this is somehow a map. And these are, so I'm talking here about a real map in the usual sense. These are countries or counties or whatever way you, regions, whatever way you want to divide the geographical entity here. And the question was, very often if you want to make a map like this, you want to make sure that the people can distinguish between the various regions, and so you would like to color them in different colors, so that the contrast shows you that this is region 1, this is another region, and so on. And the student was trying to do this for a much bigger map, and he was kind of surprised that he could always do it with 4 colors. So that's the 4 coloring problem. And he wondered whether this is also always true. That if you have a map of some very complicated, it could be a very complicated map with very divisions between suburbs or whatever you want to, can you always color this with 4 colors so that no two adjacent have the same color? Now, of course, we could have a situation like this. So, for instance, okay, again, the circle, let's say these are various quarters of a city. It could something like this. And then you could say, well, they all meet here, so they all have to have different colors. No, so when they meet in just a single edge, we don't consider them as really, they don't have borders. Okay, we only look at regions that are separated by an actual border. So these 2 regions are separated by this border. Okay, but I'm not considering these 2 regions to be separated because that's not a border, that's just a point. Okay, so in this coloring problem, how can you color this? Let's color this. This would be red, and I can make this red, and I can make this red, and then I see that I can make this green, and this green. So only 2 colors. Okay, but the question was, can you do it? Some maps, but in particular this one, I think we'll figure it out. How many colors does this map need? But the bigger problem was showing that it could always be done with 4, and that is the so-called 4 coloring problem. And the history of this is kind of fascinating. So this was a problem posed by this student, and then the student reported this to a mathematician, De Morgan, who was very much interested in it but couldn't solve it. He asked some other mathematicians, and eventually some amateur mathematician, Kemp, I think it's pronounced, I'm not so sure, found a solution, and he published it, and everybody says, oh yeah, it's solved, we can do it with 4. And then almost 100 years later, some other guy was looking at the proof and says, yeah, but wait, he made a mistake here. And this is things that happen. Mathematicians do make mistakes, and they sometimes think that they have a good proof, and they claim, oh, this is a big theorem, I have proven it, and then all of a sudden it turns out to be false. A famous example that I discussed, sometimes you might have heard it when you were taking discrete math 1, is the so-called Fermat's theorem. That is something where a lot of false proofs were given, but eventually it has been proved correctly. And honestly, I must confess, I have done the same thing. I have published sometimes a paper in which I claimed a particular problem, and afterwards it turned out it's false. I mean, people even showed, and it's a little bit embarrassing and frustrating also, because you put all this work and effort in it, and then you have to retract. But that is the way mathematics works, that's the way science works. There are steps forward, and sometimes there's a little step backward, or sometimes a big step backward, depending on how things are. Now, just to say, this happened once really to me, but other than that, I have a good track record, so don't think of me as being a shabby researcher. But okay, so all right, so yeah, okay, so then this guy finds a mistake and says, no, this is not right, and then everybody starts looking again for it, and then a couple of people, forget it, Apple and Haken, I think, they eventually provided a proof, but, and this is where the controversy comes into, the proof reduces to showing a kind of 2,000, about 2,000 different graphs. I haven't made the graphs yet. I'll get to the graph part very soon, but we will solve this with graphs. These maps are not graphs, but we will see in a sec how that relates. So they reduced it to, or let's say they reduced it to 2,000 types of maps, and then had to show by hand that each of these maps could be colored by 4 colors. Now, 2,000 cases, very complicated also. They were not simple things, they were rather complicated things that had to be colored with 4. And I said, coloring is a very difficult problem, so it is impossible for humans to do this. Computers, it would take time. I think it originally, when this was done in the, when was this done? They don't say this exactly when this was done. If I remember, it was when, like 30, 40 years ago, something. I'm not 100% sure, but perhaps a little bit. In 1976, right? Yeah. So they used computers, and so they devised an algorithm that checked on these 2,000 cases that they had to check, which they couldn't do manually, but the computer could check it for them, and the computer said, yes, okay, everyone I can color in 4. So to us nowadays it seems like, oh yeah, so we're done, fine. But at the time, and still, people are questioning this a little bit because they're saying, okay, this computer, they take perhaps a couple of days to find a solution. It's the number of data is in the millions calculations, and it's very well possible that there is a mistake. Not that, of course, a computer doesn't make a mistake. What a computer could do is a glitch, that some bit swapped into a 0, and by external reasons. There might be a thunderstorm that infects this, there might be an EMP, there might be God knows what, okay, or just quantum phenomena. So this was for a while questioned, is saying, okay, is this a valid proof? Because no human can check the proof. You need a computer to check the proof, and do we trust computers? Okay, this is all controversy, man versus machine. I think by now people are kind of convinced. One has also been able to reduce the number to 1,000, which still requires a computer. So at the moment, we have no proof that we can present to other fellow mathematicians or students that does not involve a computer. And that is very frustrating, and it's one of the first cases that we have this, and it is still considered a little bit of a controversy whether this is an actual proof or we should think of this as a potential, possible, likely proof. All right, I'll leave you with that. So how do we solve this? What is this come to? Well, we create what is from such given such a map, you can make what the book calls the dual graph. So I'll call the same thing. And what you do is, we have seen a similar thing with, remember, our very first introduction to graphs was about bridges that connected lands, basically with the same thing. What were the vertices in that thing, in the Koenig's problem, with all the bridges and walking over the bridges from various parts of the river, of the city? Remember, the vertices became the regions, the various parts in which you could walk, right? So we're going to do the same thing. So we're going to make a graph where the vertices, I'm just going to write them a little bit like this, are the regions. So let's call region A, B, C, D, E, F, G. So these become the vertices. And now we put an edge if they share a border. So the dual graph is an edge means sharing a border, neighboring. But I like to say sharing a border because I want to say these two are not considered neighbors, okay? But these two are considered neighbors because they have a border in common. So let's see what we have here for A. So A has a border with B, and it has a border with C. It has a border with D. So let's see, B, C, D, and also with a border with E. Okay. Okay, that is A. B. B has a border with A. We have that already. A border with C. A border with D. Okay. So I'm gonna go around here. Okay. E. No. C. C has a border with A, B, and D. And that's it, right? Because it's in, yeah. So, okay, so I haven't done this one, right? So we're gonna go around this here. No. Okay, that is, yeah, okay. D has a border with B. I have that. How come I don't have the border with B and D? Oh, no, this is here. Sorry, I didn't see this one. This is the border with B and D. D also borders with C. That's also have that. Right, I don't have to look at previous numbers. I just have the new ones. D has a border with E, F, and G. So it has quite a lot of borders also. So E, F, and G. You would say, Professor, why are you making such weird things? Bear with me. E. From E has a border with F. That is one that I don't have yet. And also with G. So here E and G. And then finally, F has a border with G. All right. So I hope I didn't make a mistake. And this is what happens. Now, the reason that I make this very weird, like, why do I go around? Why don't you just cross, right? Because graphs, we know that we can have edges crossed. But there are certain graphs that you can draw without crossing any edges. This is so-called planar graphs, and this is the topic just before this here. So in 10.7, that is reading, for those that are interested in, is the topic of planar graphs. So a planar graph is a graph that you can be drawn without crossings. So this is not a planar graph. Well, at least it doesn't look like a planar graph because we have crossings, but you can show, but that's not so easy again, showing that it's a planar graph is not easy, although we will prove it in a sec, that we cannot, that you cannot have any crossings. So we see a crossing here, but perhaps we could draw this without a crossing, and I think this one can be drawn without a crossing. So you have to look a little bit for it. It's not necessarily that every graph, every representation does not have crossings, but there are representations that don't have crossing. So just for instance, you might think here, let's see here the cube here, right? So if we draw the cube, we do definitely have a lot of crossings, it seems, right? You see? So this one is called Q4, I think. We have all these crossings, edges that cross, but you can also draw it this way. You have to think a little bit about it. It's not obvious that this is true, what I'm saying, that this is the same graph, but if you look at it long enough, this is the same graph. You could think of it as looking at the cube from the top with a certain kind of perspective or so, okay? So planar graphs is not an easy thing, and that's why I didn't do 10.7. Coloring is also not easy, but we can do a little bit more. So, okay, the point is that if you take a map, the dual graph is always going to be a graph without crossings. I'm not going to argue exactly why that is. It's not so hard, but read a little bit in the textbook about it. But so that is the first thing. And now the four coloring problem is about actually planar graphs, and it says the following: if G is a planar graph, a graph without crossings, then its chromatic number is at most 4. And dual graphs are planar graphs, and therefore they have chromatic number 4. Now, what does that have to do with the original coloring? Well, let's just start coloring this thing. So we do, remember, we can use the two colors, red and green again, A and B. Well, whatever color we give the vertex, we give the same color to the region. So this becomes red, and this region becomes green, and okay. And so what is the constraint of our coloring of our map? Well, neighbors should not have the same color. So for instance, let's look at C. If we look at the graph here, we see A and B. If we want to give a color to C, we have to choose a different color. There's no choice here. So again, we are trying to backtrack a little bit. We know it has to be blue. So this also means that this has to be blue. Okay? And now think about it. Any coloring of my vertices corresponds to a coloring of my map. So if I color these vertices, so D has a certain color, well, give that this color. And I'm claiming that if I can color, if this is a valid coloring of my graph, what does that mean? That means that no adjacent vertex has the same color. But what does it mean to be an adjacent vertex to this region? It means that you're bordering that region. And that's the whole point. What I'm saying is no region bordering this point has the same color. And that's what the four coloring problem originally asked. Can you color this in 4 different colors? So let's look at D here. So we see that at D connects to everything, unfortunately, that we have already, right? You can see it, sometimes it's easier to see on the map here, but it's also here, right? D connects to C, connects to B, and connects to A. So I need a 4th color here. There's no need for me to backtrack to C, because C required a new color. What color that is not relevant, right? So we need a 4th color here. So we are already at the limit of what the theorem says. Okay, so we color this region. So Now is the question, can we keep up? Can we keep up this? Let's look at E. What can we do with E? Well, what are the colors that I have available at E here? I cannot use orange and I cannot use red, but I can use, for instance, use green. So that's the first available color is green. Let's go to F. What is the first available color that I have there? Well, I excluded for me are in F is green and orange, so I can use red. So I use red. For G, G connects to D, connects to E, and connects to F. D, E, and F. That's all connected to G. And they all have different colors, so I have to use the fourth color that remains, that I still have available, that is blue. But that's the end of the coloring. I'm done. So we have to color this blue. And E had to be green. But in E, I had a choice, by the way, right? Remember, I could have done a different choice in E. The only thing that I had to stay away from it was orange and red. And F was red. So there are different ways of coloring this, but this is a coloring. And you see, pretty, huh? Well, I'm not good at coloring itself, but so here you go, a coloring problem. And so this is a planar graph, and therefore it can be done with 4 colors. That's the theorem, and we know now, trust the theorem. So there will be homework problems where you can do. This is the first application, but there are also practical applications, of course. I mean, this is a practical application, coloring a map. And for instance, suppose we have a class exam schedulings. So we have, say, I'll take the example from the book. It doesn't have to be, but let's take the example from the book. We have 7 classes, so 7 courses that needs to be scheduled, and we have various periods that we can schedule an exam. Now, the one thing that we have to do when we schedule these things, we are not concerned here about locations. We assume there are more than enough rooms to do this. The problem is more the times, and the one problem that you have to do in this scheduling is you cannot schedule a course two exams at the same time if there's a student that is in both courses. Okay, so we have the 7 courses. So 1, 2. Let me use the same order that the textbook does. Otherwise, I'm gonna get very confused with my graph. Okay. And so here, these are the 7 courses. And now we look at which courses do have, and we will put an edge, when two courses have a common student. Okay. So we're looking for those that are common students. So for instance, suppose we have 1 and 2, there's a student in course 1 and 2, there's a student in 1 and 3, there's also 1 and 4. It doesn't have to be the same student, right? So student A is perhaps in 1 and 2, student B, C are in 1 and 3, and student A, D are in 1 and 4. It doesn't matter who they are, they just have a student in common, therefore they cannot be put on the same time. That's the only restriction that we have. Okay. So, and also 1 and 7. Then 2 and 3, 2 and 4. So this is actually, so they tell us which courses are, and that's why I'm building the tree. So in the homework problem, keep that in mind. 2 and 5, 3, sorry, I mean graph. 2 and 5, 2 and 7 have one in common. Now I don't claim this is a planar graph, right? This is no longer the 4 coloring problem. Okay, so we go on 2 and 7, 3 and 4. So I'm not even trying to avoid crossings, but okay, this one, I didn't want to cross too much. 3 and 4, 3 and 6, 3 and 6. Okay, so I'm not concerned myself about crossings. By the way, whether I would draw this graph as a planar graph or as a graph with a lot of crossings, that doesn't change the coloring, the color graphic, the chromatic number. I hope this is clear. this is a point that you always have to keep in mind. The representation of a graph, which way you draw it, doesn't change the graph, and it doesn't change the properties of the graphs. Okay, except for, of course, the fact that it's planar or not, but that's something we're not talking about. Okay, so 3, 4, 3 and 6, 3 and 7. 4 and 5, 4 and 6, 5 and 6, 5 and 7, 6 and 7. So that's the graph. I think I got it. All right, let's look at this thing. So now, what is it that we got? How does coloring help us here? Well, think of the colors as the time slots, right? Red will be one particular time slot. It doesn't matter what time slot it is. Green will be a time slot that is not conflicting with the red time slot, okay? So we are coloring it with time slots, but it's easier to color things with colors, so we keep colors, okay? So red is, say, from, red could be, I'm just saying, say from 10 a.m. to 12 a.m. or p.m., I guess you would say, right? That one always throws me off. Then green would be from 12 p.m. or let's say from 10. Let's get everybody a little break here, even if you. So this scheduling problem could mean that a student has 5 exams. The only thing what we're trying to avoid here is that he has to be at 2 places at the same time. So from 10 to 11:30, let's make the exams each, and then from 12 p.m. to 1:30 p.m. And then the next color, let me see here. I'm gonna cheat a little bit. I think 4 colors suffice. I'm gonna use purple, and that is from 2 p.m. until 3:30 p.m. and then we have orange. Let's do this from 4 p.m. till 5:30 p.m. and perhaps in case that we need it, I'll put already a next possibility. No, that's not very distinguished. Blue, I don't have blue yet, so blue would be from, perhaps we need this, or perhaps we even need more, from 6 p.m. to 7:30 p.m. Let's see whether we can do it with that. Okay, so again, we start with our 2 colors, picking random 2 edges, 1 edge basically, and the 2 endpoints of that edge. Okay, so number 3. Well, 3 is an edge with 1 and 2, so I need to use a different color. So my next available color is purple. No need to backtrack here, this is what I can do. And then 4, okay, 4 also connects to 1, 2, and 3, so it has to be a different color. No choice here. So again, never backtracking to here means that's it. So what about 5? Well, 5 connects to the only ones that are colored. The ones that is colored is the green one and the orange one. So I could color it with red. So let's try to color it with red. 6. 6, what does it connect to? Already with a red one, an orange one, and a purple one. So I can make it green. Okay. And now finally, what about 7? Well, 7 connects to 2, which is green, to 1 is red. So not green, not red. Green, red, no, not that one. It also connects to purple, but it doesn't connect to orange, so I can make it orange. So we already noticed here by these 3 that the graph had, this graph here, let's call it G, had at least chromatic number 4. There was absolutely nothing we could do here. Notice, by the way, that this whole thing is these 4 together form a K4, a complete graph with 4 edges, because every 2 are connected here. And therefore, we know already that the chromatic number of a complete graph here. Okay, I did it here, but I should perhaps, I hope everybody sees that the connected number of any complete graph is exactly the number of vertices. Okay, and remember, if we have a subgraph, well, that's at least as bad. So since we have a K4 in here, we know it has to be at least 4, right? But here, this also had at least 4, but there, it didn't have a K4, by the way. This is not K4. It doesn't contain any K4. So it is not, that's not the same. But since we have a K4, we are for sure need 4, and we found 4, so we know that this is the first observation, and now we found one that has 4, so we know it is actually 4. And then also tells us when to schedule the exams. So in the first time slot, we will schedule course 1 and 5. In the second one, we go 2 and 6. In this time slot, only 3. In this time slot, 5 and 7. Okay, so that's the scheduling problem. There are other assignment applications, frequency assignments, and index registers, and so on. I leave them for you to read in the textbook. I'm going to assign some homework problems. That's, yeah, okay, all right, and I will post the solutions of the homeworks as well.